In this video, we're going to look at another type of circuit we encounter in electronics, and that's a parallel circuit. So as opposed to series circuits where all of the components are connected in series and form a loop, in a parallel circuit, the components are connected parallel to each other, so alongside each other. And there's a good example in the course notes on page 30 of how the lights on a Christmas tree work. What happens here is that rather than having a big loop of bulbs connected to each other, we connect these up in parallel, so there's different branches coming off the circuit. And the advantage of doing this should be immediately clear. If we had a circuit, I'll do a very simple one just now like this, that had 3 bulbs connected like so to a supply. As soon as one bulb went out, by breaking the circuit and all the lights would go off. And so a series circuit would not be suitable. That would also mean that when if we found some way to bypass it, which of course does exist within bulbs, we can have bulbs that go out but still allow circuit to flow, the voltage would change as well, because the voltage has to add up across all the components to the total circuit voltage. So a couple of disadvantages to a series circuit. What we can see is if we have current flowing this way, it's coming down this path and this path and this path. If we suddenly have a break in the circuit, say here, and current can no longer flow, there's nothing stopping current flowing through the second bulb, back round to the supply, the third bulb, and so on. So if one bulb goes out, our supply can continue to stay flowing through the remaining bulbs. So there's definitely advantages to different occasions where we use a parallel circuit, and there'll be other practical applications too as we go through the course. So similar to what we did in the video for series circuits, we're going to talk about the 3 important quantities for calculations in a parallel circuit. We'll talk about voltage, current, and resistance. And each stage, I'll remind you what the difference was. So I'll have a column here for parallel and a column here for series, and we can see the difference each time. So in a series circuit, what we had was the total voltage was the sum of the voltage drops across each component. And that was Kirchhoff's second law for when we had 3 component circuit. In a parallel circuit for voltage, it is the same across each branch. And what that means is that the voltage across this bulb, this bulb, this bulb, and every other bulb, the voltage across every bulb is the same as the section of circuit they're connected across. In this case, they're connected across a 240 volt supply. So there's a 240 volt voltage supplied to each of the bulbs here. And it's the same across every branch that's connected in parallel. Then if we think about current, so we had IC, same at all points. Well, we don't have that here. What we have is a current that is split up across the circuit. So we do have a circuit current. So we put an ammeter in here near a voltage. We were to put an ammeter in here. We can measure a circuit current. What's going to happen here is our circuit current is going to add up across all the branches. So there'll be a different current I1, I2, I3, I4. A different part of the current will run through each branch, and our circuit current will be equal to the sum of these. So this works like voltage worked in our series circuit. So voltage is the same across each branch, and it's current that splits up going through the different branches. And then lastly, we have resistance. Well, we saw in a series circuit that I should have written current here as well. In a series circuit, we had the total resistance was equal to each component's resistance added together. Well, in a parallel circuit, we have a completely different formula for that, where we say 1 divided by the total resistance is equal to 1 divided by resistor 1 plus 1 divided by resistor 2 plus 1 divided by resistor 3. And we do this for every single branch, the resistance of the components in each branch. So the more branches, we add, the more we lower the total resistance. Now, this is quite a cumbersome formula to work out, and we've got to do a little bit of manipulating. But the good news is that in this course, we're only ever going to have a maximum of 2 components in parallel. So we can immediately erase that. And what's further good news is, rather than having to rearrange this to get a formula that's nice and neat for getting the total resistance, we're given one in the course notes, and this is the formula here. So the total resistance in 2 parallel branches in a parallel circuit is going to be given this by this formula here. Total resistance is equal to R1 times R2 divided by R1 plus R2, and we're making a lot of use of that formula. The rules about Ohm's law still apply, so we can consider Ohm's law for the circuit as a whole if we know the circuit current and the total resistance and the voltage supply. And we can Ohm's law for individual components as well. We just need to remember important facts like the circuit current won't be flowing through every component, so we just need to make sure we don't make any mistakes with that. But these are our rules for parallel circuits, and they're different from series circuits. So we'll take care to do this correctly, and we'll use examples as we go through. So let's have a look at some worked examples of resistors in parallel. So this first example comes from page 35 of the course notes. What it says here, for the circuit below, calculate the total resistance of the parallel circuit. So the total resistance of the circuit is going to be due to these 2 resistors connected in parallel. We're given the resistances, and one thing we know straight away, because this is parallel, we cannot add them together. So we're going to need this formula, so I'm going to drag it across and we'll have a look at this. So this is our formula. The total resistance is given by R1 times R2 divided by R1 plus R2. So let's put all these values in. We're given them in the question. I'll make this slightly bigger on the screen. The text is a little bit small. So we can write RT is equal to R1, which is 270 times R2, which is 100, divided by 270 plus 100. So that's going to be equal to 27,000 divided by 370. And putting that into your calculator, you're going to find that rounds to 73 ohms. So that's how we find the resistance in a circuit like this. And that's absolutely correct. That's how we would solve a problem. But observe also that the total resistance is actually less than both resistors. And that's because when we connect up resistors in parallel, we actually reduce the resistance of the circuit. If we think back to examples of imagining our circuit like water flowing through a channel, if we have a bottleneck, which is a resistor where it's restricting flow, we open up another channel, it's still restricted, but it's another route for the current to flow through, then we're increasing the ability for current to flow, and so reducing resistance. So adding resistors in parallel reduces the total resistance of a circuit. And again, there's good reasons to do that. We don't perhaps want to have particularly high current or particularly high voltage at a certain point. And so adding resistors in this manner allows us to manipulate what these quantities are at different points in our circuit. So that's the first worked example. There's a second worked example which we'll look at now. Let's get a little bit more to it. So our second worked example, and this comes from page 36 of the course notes, looks at this circuit here. So for the parallel circuit shown, calculate the total resistance, the circuit current, and the current in each resistor. And if we hadn't remembered that already, that's a big clue for us that the current isn't the same in every resistor. It's going to be different depending on the resistance of the resistor. We know the voltage will be the same in each branch, but we'll look at this one step at a time. So what is the total resistance in our circuit? Well, we could do 1 over RT is equal to 1 over 8 plus 1 over 12, or we could just take our formula, which makes things very nice to calculate. And I'll keep this on the screen whenever I do it to show you where I'm getting it from. So our total resistance is equal to R1, which we're told is 8 ohms here, times R2, which is 12 ohms, divided by 8 plus 12. So what we're going to have here is 8 times 12 is 96, and 8 plus 12 is 20. So 96 divided by 20 is 4.8 ohms. So we've worked out the total resistance. Now, as I said in the introduction to this video, we can still use Ohm's law when we're dealing with the full circuit. So it's still true that supply voltage is equal to the circuit current, that's before it gets split into the branches, multiplied by the total resistance. And we can rearrange to find circuit current, and like so. So our current is going to be given by our supply voltage of 12 volts divided by our total resistance of 4.8 ohms. And we put that into the calculator, we're going to get 2.5 amps. Now this is the circuit current. And so to illustrate what's happening here, we imagine we've got all this current flowing through here. It's going to, some of it's going to split off down here, and some of it's going to split off up here. So let's just draw it in a bit better. What we've got is the whole current coming out here, and some of it splits off in this direction, and some of it splits off in that direction. So these two branches will have current adding up to the total circuit current we've just worked out. We want to find out what these currents are. So in part C, we're asked to find the current in each resistor. So let's think about resistor 1 first of all. Now we know, because of the rules for parallel circuits, the voltage across each of these resistors is the same as the supply. So voltage 1 is equal to 12 volts. That's also what voltage 2 is. And our resistance is given here is 8 ohms. And we just need to find the current across resistor 1. But we can just again use Ohm's law. We can always apply Ohm's law to an individual component when we know two of these three things. So I1, the current running through that branch there, is equal to V1 divided by R1, which is equal to 12 divided by 8, which is equal to 1.5 amps. And now we can have a look at what the current in I2 is. So we could do the exact same thing because we know we have a voltage 12 volts and we have resistance. We could also remember what we know about current in a parallel circuit and say the total circuit current is equal to I1 plus I2. We worked out that the total current for the circuit was 2.5 amps. We've just worked out I1 is 1.5 amps plus I2. So subtracting 1.5 from both sides tells us the current running through the second resistor must be 1 amp. And that concludes the example. And if you look at the course notes, you'll see they've tackled it in a slightly different way from this, but again, there can be more than one route to the correct answer as long as we're using our correct conditions and rules to calculate the expression. And this, I probably should have mentioned this, I'll write it back up at the start. This is what we call Kirchhoff's first law. So we had Kirchhoff's second law for, see, this is Kirchhoff's first law here about the total current is going to equal to sum of the current in each of the branches added together. And that concludes the remaining worked example. You can now move on to the exercises, which are on page 37 and the top of page 38. And there will be a separate video showing work solutions for those as well.